Download this code from codegive.com, link in the description below. Memory allocation failure, a comprehensive guide with code examples. Memory allocation is a fundamental concept in computer programming, especially in languages like C and C++ where manual memory management is required. Understanding how memory allocation works and how to handle potential allocation failures is crucial for writing robust and reliable software. This tutorial will delve into memory allocation failure, covering its causes, detection, and, most importantly, handling strategies with practical code examples in C. 1. Understanding memory allocation. Before discussing failures, let's briefly recap how memory allocation works. In C and C++, memory allocation primarily involves requesting blocks of memory from the operating system's heap. The heap is a region of memory available for dynamic allocation and deallocation during program execution. The standard C library provides two main functions for dynamic memory allocation. *malloc, size_t size, asterisk allocates a block of memory of the specified size, in bytes. Returns a pointer to the beginning of the allocated block if successful, or null if allocation fails. The allocated memory is uninitialized. *calloc, size_t number, size_t size, asterisk allocates a block of memory for an array of number elements, each of size bytes. Returns a pointer to the beginning of the allocated block if successful, or null if allocation fails. The allocated memory is initialized to 0. Correspondingly, you must use the free function to release memory which has been allocated using these two functions. 2. Causes of memory allocation failure. Several factors can lead to memory allocation failures. Insufficient system memory. The most common cause is that the system simply doesn't have enough free memory to fulfill the allocation request. This can happen when other programs are consuming a large portion of available RAM, or if your program itself has already allocated a significant amount of memory. Memory fragmentation. Over time, repeated allocation and deallocation of memory can lead to fragmentation. Fragmentation occurs when available memory is broken up into small, non-contiguous blocks. Even if the total amount of free memory is sufficient, the allocator might be unable to find a contiguous block large enough for the requested size. This is especially problematic for larger allocations. Heap corruption. If your program writes to memory outside the bounds of an allocated block, example writing past the end of an array, or performs invalid operations on the heap, example double freeing memory, it can corrupt the heap's internal data structures. This can lead to allocation failures or, worse, unpredictable program behavior. Operating system limits. The operating system may impose limits on the amount of memory that a single process can allocate. These limits are often configurable but can prevent large allocations from succeeding. Resource leaks. A resource leak occurs when resources, such as memory, are allocated but never properly released. This gradually depletes available resources, ultimately leading to allocation failures. The most common resource leak is a memory leak, forgetting to free allocated memory. 3. Detecting memory allocation failure. The key to handling memory allocation failures is to detect them properly. Both malloc and calloc return null when they fail to allocate the requested memory. It is absolutely crucial to check the return value of these functions before using the allocated memory. Best practices. Always check for null. Make it a habit to always check the return value of malloc and calloc for null immediately after the allocation call. This is the most important step. Error handling. If allocation fails, handle the error gracefully. Do not attempt to use the memory pointed to by the null pointer. Instead, print an error message, using fprintf, str, to send it to the standard error stream, perform necessary cleanup, and exit the program or take alternative actions, discussed below. 4. Handling memory allocation failure. When a memory allocation fails, you have several options for handling the situation. The best approach depends on the context of the allocation and the severity of the failure. A. Error reporting and termination, simple approach. For many simple programs, especially those that are not mission critical, the simplest approach is to print an error message and exit the program. This is shown in the examples above. This is a reasonable approach if the program cannot function correctly without the allocated memory. Advantages: simple, easy to implement. Disadvantages: program terminates, potentially losing data or interrupting user activity. Not suitable for programs requiring high availability. B. Graceful degradation. In some cases, it's possible to continue the program's execution even if a memory allocation fails. This is called graceful degradation. This usually involves reducing functionality or using alternative data structures that require less memory. Advantages: program can continue to function, albeit with reduced functionality. Disadvantages: requires more complex logic to handle the different states. May not be applicable in all situations. Careful design is required to ensure that the program functions correctly in degraded mode. See retry allocation. In some situations, a temporary memory shortage might be the cause of the allocation failure. You could try to allocate the memory again after a short delay. This approach should be used with caution to avoid an infinite loop. Advantages: can potentially succeed if the memory shortage is temporary. Disadvantages: adds complexity. May not be effective if the memory shortage is persistent. The sleep function can make your program less responsive. Requires a maximum retry count to prevent infinite loops. D. Memory pool/arena allocators. For applications that frequently allocate and deallocate small objects, using a memory pool or arena allocator can improve performance and reduce fragmentation. A memory pool pre-allocates a large block of memory, which is then divided into smaller, fixed-size chunks. When an object is needed, a chunk is taken from the pool. When the object is no longer needed, the chunk is returned to the pool. This eliminates the overhead of calling malloc and free for each object and reduces fragmentation. If the initial pool allocation fails, you can implement a strategy as above to handle that single, potentially larger, allocation. Here is a basic example of a simple memory pool. Advantages: reduced fragmentation, improved performance for frequent small allocations. Allows central management and error handling for memory blocks. Disadvantages: requires more complex implementation. Fixed block size may not be suitable for all objects. More code to debug and maintain. E. Virtual memory techniques, advanced. Operating systems provide virtual memory, a powerful feature that allows programs to access more memory than is physically available. When physical memory is exhausted, the operating system can swap portions of memory to disk. You might consider using larger allocations with the expectation that the OS virtual memory will manage pages efficiently. Note that excessive swapping can severely degrade performance. This approach is not suitable for real-time or performance-critical applications. 5. Preventing memory allocation failure. While it's essential to handle allocation failures gracefully, it's even better to prevent them from occurring in the first place. Here are some strategies for minimizing the risk of memory allocation failures. Allocate only when necessary. Avoid allocating memory unnecessarily. If you can use statically allocated variables, global or local variables, instead of dynamic allocation, do so. Use efficient data structures. Choose data structures that minimize memory consumption. For example, consider using bit fields or compressed data formats. Avoid memory leaks. The most important step is to ensure that you always free memory that you have allocated with malloc or calloc. Use tools like valgrind or address sanitizers /asan in compilers like GCC and Clang, to detect memory leaks. Keep allocations small. Avoid allocating very large blocks of memory if possible. Break large tasks into smaller chunks and process them sequentially. Check array bounds. Prevent buffer overflows by carefully checking array bounds. Buffer overflows can corrupt the heap and lead to allocation failures. Use smart pointers. C++. If you are using C++, consider using smart pointers, example std unique_ptr, std shared_ptr, to automatically manage memory and prevent memory leaks. This is a very important strategy for avoiding memory management problems in C++. Limit recursion depth. Deep recursion can consume a significant amount of stack space. If your program uses recursion, ensure that the recursion depth is limited to prevent stack overflows. Monitor system resources. Use system monitoring tools to track memory usage. This can help you identify potential memory leaks or excessive memory consumption. 6. Tools for debugging memory issues. Several powerful tools can help you detect and diagnose memory-related issues, including memory leaks, heap corruption, and allocation failures. Valgrind. Linux Valgrind is a suite of debugging and profiling tools for Linux. MEMC Valgrind's memory error detector, is excellent for finding memory leaks, invalid memory accesses, and other memory-related problems. Address sanitizer. ASAN address sanitizer is a fast memory error detector that is built into compilers like GCC and Clang. It can detect a wide range of memory errors, including heap buffer overflows, stack buffer overflows, use after free errors, and memory leaks. Memory profilers. Tools like perf, Linux, and Visual Studio's profiler can help you identify areas of your code that are consuming the most memory. Static analyzers. Static analysis tools can analyze your source code and identify potential memory-related errors without running the program. Examples include Covariety, PVS Studio, and Clang Static Analyzer. 7. Conclusion. Memory allocation failure is a common problem in C and C++ programming, but it can be effectively handled by understanding its causes, detecting it properly, and implementing appropriate handling strategies. By following the best practices outlined in this tutorial and using debugging tools, you can write robust and reliable software that handles memory gracefully. Remember that the most important takeaway is, always check the return value of malloc and calloc, for null. Failing to do so can lead to unpredictable and difficult to debug program behavior. Use smart pointers when possible in C++. By applying these techniques, you can significantly improve the stability and reliability of your applications.